For today's lesson, you'll learn how to get started quickly with the Google Firebase and have it connected with your ESP32. I'll show you the step-by-step process of how to create a project to store and read values from the Firebase Realtime Database with your ESP32. Of course, we'll be using the Arduino IDE in writing codes for your ESP32 to demonstrate these operations in your real-time database. At the end of this lesson, you should be able to conduct your own experiment to save input data of various types like integer, float, and boolean coming from an analog sensor such as a photoresistor or from digital data such as a switch, as well as be able to read this stored data from your real-time database to control devices that are attached to your ESP32. Hi, my name is Joe Edgo, and welcome to Lesson 5 of the IoT Development Training course with ESP32. For this experiment, you'll need the following materials: 2 LEDs and 2 current limiting resistors, a light-dependent resistor or LDR, a momentary normally open push-button switch, 2 10 kilo ohm resistors, and your ESP32 development board, a breadboard, and a couple of connecting wires. To start our circuit connection, ensure that the ground and the 3.3 volt supply of your ESP32 development board are connected to your breadboard's negative and positive bus strips. Then, we'll use the GPIO 12 and GPIO 14 to connect the 2 current limiting resistors and the LEDs. And then, the GPIO 36 will be used to receive an analog input from our photoresistor through a voltage divider circuit, also known as a potential divider. Please note that there are 2 configurations for this circuit depending upon the position of the LDR within the potential divider network. With our configuration here, the voltage output, represented by this orange wire, increases as the light received by this LDR increases. And finally, the tactile switch with one of its pins connected to the 3.3 volts and the other pin is pulled down by this 10 kilo ohm resistor. Here, we'll use GPIO 13 to accept this digital input signal. So, let's plug this into our computer and start working with Google Firebase. So, what is Firebase? Firebase is Google's mobile application development platform that helps you build, improve, and grow your app. It has many services used to manage data from any Android, iOS, and web application. So, Firebase is a complete toolset that includes things like analytics, authentication, databases, configuration, file storage, push messaging, and so on. Most importantly, the services are hosted in the cloud and scale with little to no effort on the part of the developer. So, in this demonstration, we'll create a Firebase project with a real-time database and we'll use the ESP32 to store and read data from that database. Through Firebase, our ESP32 can interact with the database from anywhere in the world as long as it is connected to the internet. To start, open your browser and then go to firebase.google.com. To create a new project, you must sign in using your Google account, and then click the Get Start button. And then, click Add Project to create a new project. Here, you can give any name to your project. I'll name mine Lesson 5 ESP32 RTDB, and then click Continue. Next is Google Analytics. Although this is free and unlimited, we will not be using this feature for our current project, so I'll disable this option and then click Create Project. This could take some time to set up your project. And once your project is ready, click Continue. And you'll be redirected to your project console page. Next, you need to set up the authentication method. This takes care of logging in and identifying the users of an app. In this case, the user is ESP32. Knowing a user's identity allows an app to securely save the user's data in the cloud and provide the same personalized experience across all the user's devices. On the left sidebar, click Build, Authentication. This section allows your project to authenticate and manage users from a variety of providers without server-side code. Click Get Started. In the Sign-in Method tab, you'll see several sign-in providers to choose from. You can sign in using email password, phone, Google account, Facebook account, GitHub, and others. For testing purposes, I'll select the anonymous sign-in. By enabling anonymous guest account in our application, it enforces user-specific security and Firebase rules without requiring user credentials. So, click Save. Next is to create a real-time database. So, click Build, Real-Time Database, and then click on Create Database. And then, select the location where your real-time database data will be stored. Ideally, it should be the closest to your location. I'm from the Philippines and I'll choose Singapore. And click Next. And then, set up the security rules for your database. By default, the Start in Lock mode is selected, and it says here, your data is private by default. Client read-write access will only be granted as specified by your security rules. However, for testing purposes and for quick setup, I'll select Start in Test mode. And with this, our data is open by default, and we must update our security rules within 30 days to enable long-term client read-write access. In some of my later videos, I'll show you how to secure your database using database rules. So, click Enable, and your real-time database is now created. Now, copy and save this database URL in a notepad because we will need it later in our ESP32 code. Another thing that we need to get is this project's API key. So, to get your project API key, click this gear icon on the left sidebar and select Project Settings. In the General tab, you'll see the important information about your project. And the one that we need here is this Web API key. Again, I'll copy and save this to my notepad. So just a reminder, secure this information only to yourself. I am only showing you this publicly for demo purposes only, and I'll be deleting this project after I made this video. So now, we are ready to connect this real-time database with our ESP32. To begin, open your Arduino IDE, then go to Tools, Manage Libraries. Here, we need to install the Firebase ESP client. Choose this Firebase Arduino client library for ESP8266 and ESP32 by Mobist. Select the latest version and click Install. And once done, click Close. First, we need to include the required libraries. We'll use the Wi-Fi.h to connect the ESP32 to the internet, and the Firebase ESP client.h to interface the ESP32 with Firebase. We also need to include the following Firebase add-ons libraries: the token helper for token generation, and the RTDB helper for real-time database payload printing and other helper functions. Then, we need to define our network credentials. My Wi-Fi SSID is Jogo Galaxy with password of 12345678. Of course, use your own Wi-Fi network credentials. Now, we need to define here our project's API key. This is the one that we've copied earlier. Also, the database URL, in case you've forgotten it, you can get it here. Then, from our circuit board, we'll define the LED 1 pin at GPIO 12 and the LED 2 pin at GPIO 14. And then, the LDR pin is at GPIO 36. So, let's create some variables. First, we need to create the 3 Firebase objects that we need. The Firebase data, this will handle the data when there's a change on a specific database node path. The Firebase auth, it is needed for authentication. And the Firebase config, which is required for configuration. Then, this sendDataPrivMillis variable is needed for our millis function later, so that we can read and write to Firebase database at a specified interval in a non-blocking way. Then, the flag variable, signup_OK, that we're going to use later as well when we have a successful signup. And then, an integer LDR data to store the 12-bit ADC value from 0 to 4095. And finally, a float voltage to get the equivalent voltage of the LDR data. In the setup function, we initialize the serial communication and then connect to the internet using the SSID and password we defined earlier. And then print a message connecting to Wi-Fi. Now, I'll check a condition here that if the Wi-Fi is not yet connected, just print a single dot every 300 milliseconds. And once connected, get out of the loop and print the assigned local IP to our ESP32. Next, we need to specify the API key in our Firebase configuration object, as well as the database URL. Then, we call the Firebase signup method. Here, we pass in the Firebase config and the Firebase auth objects. The last two arguments are empty strings. This denotes an anonymous user signup. Note that in the anonymous user signup, every time the ESP32 connects, it creates a new anonymous user. Then, if the sign-in is successful, we set the signup_OK variable to true. If it fails, then we print the signup error message. We also need to add the following configuration object. Assign the callback function to the long-running token generation task. Please check the add-ons tokenhelper.h for more info. And then, we initialize and begin the Firebase library with the same configuration and authentication settings we defined earlier. Inside the loop function, what we really want is to send data to the database periodically. To do this, we check if the Firebase is ready, and if signup is successful, and we do this periodically every 5 seconds, or at the start of this loop. Note that we need to reassign a new millis value to this sendDataPrivMillis variable every time it exceeds the 5-second interval to restart the 5000 millisecond counter. Now, to store the sensor data in our real-time database, first, I'll read the analog data from my LDR pin. Note that this is of type integer. I also want to get the analog voltage reading and store it to the voltage variable, and this is of type float. So, I'll divide it by 1000 to convert the millivolts to volts. Now, this is how we store the actual data in our real-time database. As mentioned in the library documentation, to store at the specified node in the Firebase Realtime Database, use the following functions: set, setInt, setFloat, setDouble, setString, setJSON, setArray, setBlob, and setFile. These functions return a Boolean value indicating the success of the operation, which will be true if all the following conditions are met. The server returns HTTP status code 200. The data types match between request and response. In our program, we will send an integer data, so we need to use the setInt function as follows. The first argument is the Firebase data object. The second argument is the database node path. Here, you can choose any database path you want. If the path does not exist, it will be created automatically. And the last argument is the value we want to pass to the database path. In this case, we are passing the value saved in the LDR variable. So, if the setInt is successful, we'll simply print the LDR data, the data path where it was stored, and the data type used to store it. If it failed, then we'll just print the error reason. Note that we can store multiple data of different types to different node paths. So, we'll store this voltage of type float. I'll duplicate this code and simply change the database node path to sensor voltage. Also, instead of LDR, it should be voltage. Now, for float data type, we'll use the setFloat function. And that's it. So, let's compile and upload our code. And there's a missing double quote here. And the callback must be a small letter b. So I'll open my serial monitor to check the status. And it looks good. Our ESP32 is consistently sending two values of type int and type float to our real-time database. So let's check this in the actual Firebase Realtime Database console. And here you go. Our database has one sensor node. And this node has two nodes, LDR data and voltage. You'll notice that the database blinks when a new value is saved. In this case, it could happen every 5 seconds. You might want to adjust yours accordingly. So, if we read a value that doesn't change after the specified time, then you will not see the node blink. Here, I'll focus a LED light to my LDR and notice that the LDR data read and its equivalent voltage read increased significantly, reaching up to 2 volts. Then, removing it drops the sensor reading back to about 0.5 volts. Now, blocking this sensor with my finger significantly drops the LDR data read and ultimately reaches 0, which means total darkness. And that's it. Congratulations! You've successfully stored sensor data of different types into the Firebase Realtime Database using the ESP32. Next, we'll read values from this real-time database and make use of that data in our ESP32 to control the two LEDs. In the Firebase Realtime Database, data is stored as JSON objects. We can think of this database as a cloud-hosted JSON tree. There are no tables and records, which means it is a NoSQL database. When we add data to the JSON tree, it becomes a node in the existing JSON structure with an associated key. So, I'll put here LED as my key. And under it, I'll add another node. I'll give it a key, analog. Now, data stored can be represented as certain native types in the database that corresponds to available JSON types to help us write more maintainable code. I'll put a value of 0, and Firebase automatically detects this as numeric type. Under the same LED node, I'll add another node with the key digital. I'll put an initial value of false, and it is automatically detected as Boolean. You can always click the icon beside the value to select the appropriate type you want to use. So, what we want to do here is that we control one of the LEDs connected to our ESP32 through pulse width modulation, depending on the integer value we placed here. Say, 8-bit resolution means 0 to 255. And the other LED, we will control it digitally through a Boolean value of either true or false. Now, we go back to the Arduino IDE and write codes to read this node's data in real time. I'll remove one of the print lines here so it is more organized. First, I'll define the PWM channel 0 and then define a constant frequency of 5000 and a constant resolution of 8-bit. And then, I'll declare an integer variable PWM value and initialize it to 0. We'll use this to store the data that we will be reading from the database LED analog node path. Next is a Boolean LED status. We'll use this to store the value that we will be reading from the database LED digital node path. And then in the setup function, I'll initialize the LED 2 pin as output. However, for the LED 1 pin, I'll use the LED C setup. And then, attach it to my PWM channel. Inside the loop function, If you want that the data reading happens every loop so that the two LEDs will change their status instantaneously as the database value is changed, you can put your codes outside this millis if block. The code is fairly similar to the previous code that we use to store data to the database, but instead of setInt, I'll use getInt. And the node path is LED analog. Also, we need to include additional conditions here to check its data type. If it is of type int, I'll get the int data of this Firebase database object and then store it in the PWM value variable. And then, I'll print a successful read message and specify the data path. I'll concatenate the PWM value and its data type. Now, we control the LED1 using the LEDCWrite function with this PWM value. However, if data read is not successful, we print failed and display the error reason. Now, I'll duplicate this code and change this getInt to getBool. I'll also change the node path from LED analog to LED digital. And then, check the object's data type if it is Boolean. If so, use the LED status variable and assign the bool data of the red Firebase database object. I'll change this print PWM value to LED status. And instead of LEDCWrite, I'll simply use the digital write function and control LED2 with this LED status value. And that's it. Let's upload the code and test. And as you can see here in the serial monitor, the data readings for the LED analog and the LED digital nodes is happening very fast. A couple of successful reads in just under a second. Much better if we place this code inside a timer or millis so that it only reads at a specified interval. So let's re-upload the code. And this is much better. We can clearly see the two data saved and the two data read to and from the Firebase Realtime Database. Now, going back to our Firebase console, let's test both the saving of the sensor data and the reading of the LED node data. If I focus this light to my LDR, still, the LDR data gets updated, increasing its value. Now, if I manually change this digital false value to true, the LED2 turns on. If I change this back to false, then LED2 turns off. In the LED analog node, if I change this to 32, LED1 turns on, but the light intensity is a bit dim. You can see this clearly if I turn on the LED2 using the digital write function. And let's try increasing the PWM duty cycle value to 96. And the LED is a bit brighter now, but you can still recognize the brightness difference between the two LEDs. So, changing this to 255 gives a full 3.3 volts. And LED1 is now similar to LED2 brightness. So, to practice your skills in Firebase Realtime Database and ESP32, try to implement a similar circuit with a slightly different database node paths and values. You'll be adding another node called switch under the sensor node. Its value must correspond to the physical tactile switch placed in your breadboard. If the switch is pressed, the Boolean value of true is saved. However, if the switch is not pressed, the Boolean value of false is saved. The LDR data and the voltage nodes remain the same. Once the LDR receives light, the LDR data and voltage values stored increase. Similarly, the digital node's true or false value directly controls the LED2's on and off behavior. However, in the LED analog node path, Instead of using an integer value as PWM duty cycle, use a float data type. And then, you can use values from 0 up to 3.3 volts to adjust the brightness of LED 1. Again, thank you very much for watching, and I hope that you've learned something of value here. To support this channel, please click the like and subscribe button, and don't forget to hit that bell icon to get notifications for every new video I uploaded for this course. See you again in the next lesson.